Hello, I hope you guys are doing really well, and this should be Tuesday for you. Hopefully you did really well on the 11.1 quiz, and then you took notes on 11.2 on your own, and now you're watching this video. Please add to your notes, and then after you watch this video, there will be a short little Google form for you to just go on, click, yes, I did this. I might ask you some random weird question. So, be listening out during the video so you know what that weird question might be about. So let's go ahead and get started with 11.2, and we're talking about the conservation of energy. And I want to talk for a few moments about that word conserved, because it means something different based on like how we usually use it in our society versus what it means in this physics chapter. And so when we talk about conserving things, just in the real world, like maybe you're supposed to conserve water, we're supposed to conserve our natural resources. When we say it in those terms, what we mean is we want to use as little water as possible. Like we don't want to waste. Or if we conserve our natural resources, we don't want to waste our natural resources like oil deposits and things like that. We don't want to use them up too quickly. And so that is not what the term conserve means in physics. Okay, in physics, basically it means that you don't lose any of it. And so as energy is changing forms, if you don't lose any energy, then we say that it is conserved. Now, what we mean by losing energy can mean a couple of different things too. Like ideally, if we had potential energy and kinetic energy, it would be translated into another usable form. Like for instance, if I use energy to put something up on a shelf, it has potential energy, but that potential energy is usable. Like I could make it fall and like activate something else that I wanted it to do or whatever. So a lot of our energy conversions convert energy into what we would say is a usable form. A lot of energy conversions though go into what we would say is an unusable form. Like if I clap my hands, okay, I'm using chemical energy in my body that's stored up to make my hands move, which is kinetic energy. And then every time my hands clap, that sound is also energy, and it's making the room vibrate and it dissipates. But the sound itself is what we would call unusable energy or unrecoverable energy. So I want to make sure that you understand that when we talk about energy being conserved, we usually mean that it's translated completely from one form to another with no energy lost to unusable forms. So wanted to clear that up. And then like in a close, like the law of conservation of energy says energy cannot be created or destroyed. So no matter how many times energy changes forms, it's still present, it's just in different forms, and those forms may or may not be usable. So just keep that in mind. Okay, so let's talk about mechanical energy. Okay, I have these prepared, so some got scraped off a little bit. But hopefully you wrote some things in your notes about mechanical energy. And at first it sounds a lot like thermal energy, because thermal energy is the sum of kinetic and potential energy. But when we're talking about thermal energy, we're talking about more of an internal energy. And so if I take my notes, for example, if I'm talking about the thermal energy of this paper, I'm talking about the energy within the particles of matter within the paper. When I'm talking about mechanical energy, though, I'm doing it on the macro level, and almost always the thing in question is moving many times when we talk about mechanical energy. And so the symbol is ME, and the unit is the joule, just like all the other forms of energy. And here's the formula. Okay, you've got mechanical energy is equal to the kinetic energy of a system, and that would include both linear kinetic energy and rotational kinetic energy. Like if something is spinning or you're twisting something and it's moving in a circular pattern, both of those would count. You wouldn't count the kinetic energy of the particles of matter inside the thing, just like the physical movement, the translational kinetic energy or the rotational. And then the potential energy that we would count in this would be gravitational potential energy, like maybe something can fall, or elastic potential energy, like a hairband has been pulled back, or a spring is coiled and you're going to release it later or whatever. And so those kinds of potential energies would be counted for this, not like energy due to chemical bonds or the way the atom is structured, not that, only these two. And so make sure that you update your notes so that you understand that really clearly. Okay, so when we have a closed, isolated system, that means like nothing's coming in, no matter's coming in or going out, no forces are affecting it from the outside, no energy is leaving the system or coming in whatsoever. The initial kinetic energy plus potential energy, in other words, the initial mechanical energy, is equal to the final. And then we're going to look at the way that energy can be translated from one form to another, and we'll see how the totals of these should be the same. Now, in real life, do we have closed, isolated systems? Not really. Like, some people would consider the entire universe a closed and isolated system, but we know that it's really, really hard. Even if you have like a Yeti cup and it's so well insulated, it's really hard to say that that is indeed a closed and isolated system. And so a lot of the things that we talk about are theoretical, and I'll explain more about that as we go along. So I want to look at, actually, if you have your book, and if you don't have your book, you can pause it. That's the beauty of video. You just pause it really fast. Find your book. We're going to be on page 303 because I want to run down some of these energy transitions. And it's backwards to me, so I might have to like keep turning it around so I can see. But the top one, sorry, this is like, so hang on. Let me see if I can prop this up a little bit better. All right, so we're on page 303. It's a little bit better. Okay, so this is clearly a roller coaster. We had fun when we got to go to Busch Gardens on some of these. But at the top of the roller coaster, I really like this graph down here because it's showing that almost all the energy in the system is potential energy because of the height. And then as it goes, as the people, I guess there's more than one person in here, whatever. So we'll just say the cart, as the cart is going down the hill, like now at this point, it's no longer as high. So it doesn't have as much potential energy, and it does have some kinetic energy. And then at the bottom of this hill, they're considering this 0, I guess, for the reference level. So it's got like no potential energy right now compared to the reference level, and then the maximum amount of kinetic energy. And then you'll notice that up here, some energy gets lost along the way. Like, how does energy in a roller coaster get lost? Well, no roller coaster is silent, so obviously sound is one of them. It's on a track of some sort, so there's a lot of friction, so it's losing thermal energy. And so unless there's some kind of motor, the second hill can never be as high as the first one, and then you can continue to follow that through. So that was a roller coaster example. The next one is very similar. It's got a skier skiing down a slope, and then you can also check out the pendulum one at the top of its flights, which would be the ends. That's the maximum height it's going to reach. And so the potential energy is the greatest at the ends. And then when it's at the bottom, it's at 0 reference level. So it's got no potential energy for that millisecond, but it's got maximum kinetic energy. And you can see as it swings through, energy is being converted along the way. Now, even like in a pendulum, you do better for a while, but it's going to eventually slow down because it's tied with a string, and that string has probably some friction as it's moving and things like that. Also, there is air resistance because you're not doing it in a vacuum. That would be really expensive if you figured out the mechanism to do the pendulum in a vacuum. But anyway, you get the idea of those energy conversions. Okay, so when we talk about energy converting, we're also going to talk about what happens when things run into each other. So we're going to do some math in a different video because that would make it super long if we tried to do the math today. But I want to spend most of the rest of this video talking about types of collisions. So hopefully you saw that and you already have them recorded in your notes. So remember, just add information that you did not already have. And it may not even be something I wrote down, but you know it's important, so add it in. And so the first type of collision would be an elastic collision. And you may have heard this term before in chemistry because we talk about ideal gases having elastic collisions. And so in an ideal gas, the idea is you have all these gas particles flying around, and as they hit each other, they're going to bounce off and they're not going to lose any kinetic energy. And so we say that that's a property of an ideal gas. And the truth is, most gases actually behave like ideal gases unless they're under really high pressure or they're really, really cold. So that's pretty cool. But when objects hit each other, in physics, you're really not going to get true elastic collisions where the initial kinetic energy is equal to the final and there's zero loss of energy. If something hits something else, it's probably going to make a sound. For this to happen, they would have to bounce off each other and keep going as if nothing happened. And so this isn't going to be very common in real life. This is more of a theoretical type situation for solid objects. The things that would come closest to this, like if we wanted to do a physics experiment, would be really solid, hard objects like pool balls or billiard balls. I don't know why it's called pool sometimes and billiard sometimes, whatever. Billiards just sounds more fancy. But if those hit each other, you're definitely going to hear that cracking sound, like a big crack, and then they're going to bounce off each other. They're on that felt pad on the pool table, so they're going to have a reduced amount of friction. There still is friction, obviously, but something like that, or like maybe two steel ball bearings, those hitting each other, things like that are really solid, hard, would even maybe have a lot of momentum. So those are going to be the best at approximating what we would say was an elastic collision, but this is a theoretical thing for most objects. Okay, so the next type of collision would be a perfectly inelastic collision, and in this case the initial kinetic energy is greater than the final, so some energy has been lost, and the particles, because this is a perfectly elastic one, are going to collide and stick together. So they are not going to bounce off. They're going to essentially become one object or be treated as one object, even though you could physically see the two objects still. For example, let's say that you have two cars that collide and come to a stop and they just kind of mangle and stick together. That would be a perfectly elastic collision because the initial kinetic energy was a lot more than the final kinetic energy. And then it got rubbed off a little bit, but inelastic collisions, this is basically the same thing as the perfectly elastic, except we didn't have the condition where they stuck together. Like maybe two cars collided with each other, and instead of sticking together, they now have dents or whatever in them, but they're now like separated. They kind of bounce off each other a little bit, but definitely the final energy of the final kinetic energy of the system was less than the initial kinetic energy. So inelastic and perfectly inelastic are really close. It's just that in the perfectly inelastic, they definitely stick together, and then in the inelastic, they won't stick together. And then we have super elastic collisions. Okay, this doesn't seem possible because the final kinetic energy is greater than the initial kinetic energy, and everybody knows that energy cannot be gained or lost, created or destroyed. So like energy can't be created or destroyed, the law of conservation of energy. And so the way that this works is during the collision, like some other energy was converted to kinetic energy. So it could be potential energy that was stored up, like maybe a spring was all cocked, ready to go, and when things collided, the spring also released, and so potential energy went into the system as kinetic energy. Or perhaps like there was a bomb that blew up, like somebody stepped on a landmine. That's kind of gross, sorry, but all that potential energy that was just waiting was released, and so obviously the step wasn't that much kinetic energy, but the releasing part, because it was stored up with all that potential chemical energy, that's going to be a greater final kinetic energy. And so the only way this would happen is if you had a situation where you had some potential energy or some other kind of energy that could be released that was just waiting for that collision to happen. So those are the different types of collisions. And I'm going to give you a word of the day so that when you're filling out your form that says you watched the video, you know to put this word down. So your word of the day is orange, O-R-A-N-G-E. Why? I don't know. It just is. So correct your notes, respond to the form, and then tomorrow we'll do some math.